Volcanoes are an essential part to human life. They created the Hawaiian Islands, they destroyed Pompeii, and they hindered air travel for 3 weeks. They were made into religious symbols, and they even drastically changed the global temperature. But why would we be so unaware of them? Why would tsunamis and cyclones hold higher importance than volcanic eruptions? Well, one reason would be the low prevalence of active volcanoes in Hong Kong. Hong Kong is largely safe from volcanic eruptions. Yet there are still reminiscences of volcanic eruptions millions of years ago. The highest mountain in the city, Tai Mo Shan, is an extinct volcano, which last erupted in the Jurassic Age. There have also been discoveries of volcanic rocks and rock formations near the High Island Reservoir. From this, it is clear that such volcanoes have shaped Hong Kong's land. But how? How volcanoes formed? Why and how do they erupt? How do they affect us? Simply speaking, a volcano is any area on the planet where material from the interior of the planet makes its way to the exterior. On Earth, this material is called magma, or fluid molten rock. It's a very complex mixture that contains solids, liquids, and gases. In order to understand how this makes its way outside, we will need to take a look at the structure of Earth. The Earth is composed of many layers, which are divided roughly into the core, the mantle, and the outer crust. We all live on the rigid outer crust. It is very thin, like the outer skin of an apple. Directly under the outer crust is the mantle, the largest layer on the Earth. The mantle is extremely hot because of the radioactive isotopes, but for the most part it stays in solid form because of the pressure deep inside the planet is so great that the material can't melt. The core is the center of the Earth. We usually don't talk about it when discussing volcanoes because it is so far removed from the action. The interesting part comes from a theory called plate tectonics. This theory holds that the lithosphere, a layer of the crust that comes in contact with the mantle, is separated into multiple plates. These plates float on the mantle on a layer called the asthenosphere, and where these two layers interact is where the most interesting volcanic activity happens. If we look at a map of the plates and the borders, we can see that most volcanoes happen on these lines. However, these plates must interact with one or two ways to produce volcanic activity. If the two plates are moving away from each other, the mantle rock from the asthenosphere layer below comes up into a void and melts between the plates, forming magma. As the magma flows out, it cools, hardening to form new crust. This fills in the gap created by the plates diverging. This sort of magma production is called spreading center volcanism. At the point where two plates collide, one plate may be pushed under another plate so that it sinks into the mantle. As the rigid lithosphere pushes down into the hot, high-pressure mantle, it heats up. Many scientists believe that the sinking lithosphere layer can't melt at this depth, but that the heat and pressure forces the water, the surface water, and water from hydrated minerals out of the plate and into the mantle layer above. This increased water content lowers the melting point of the mantle rock in this wedge, causing it to melt into magma. This sort of magma production is called subduction zone volcanism. But what about volcanoes like Hawaii, nowhere near a plate boundary? These are caused by mantle hotspots. Magma simply bursts through the crust and builds up islands, or chains of islands. The main differentiating factor between explosive and oozing eruptions is the viscosity of the magma. Thinner, runnier magma leaks gases and spreads out faster, increasing the surface area and cooling faster. Thicker, gooier magma can trap the gases and stay compact, building heat and pressure until one critical moment. But what determines the viscosity of the magma down at the bottom of the causative chain? This has to do again with the interactions between the tectonic plates. Spreading center volcanism, that we talked about earlier, pulls magma from the mantle, causing a vacuum. This tends to result in a slower magnetic action and calmer eruptions relatively. Subduction zone volcanism pushes the magma out by creating a high-pressure zone. This high-pressure conjunction of plates forces minerals into magma, most notably silica. High silica content means high viscosity, as it acts as a bonding agent. So now that we know what makes a volcano explosive, how do we measure explosiveness? Well, we use the VEI scale, which runs from 0 to 8. It relies on how much material is thrown out, to what height, and how long the eruption lasts. The scale is logarithmic, which means a VEI2 eruption is 10 times as powerful as a VEI1 eruption. One of the most recent major volcanic eruptions is the 2010 eruption of Eyjafjallajökull, a small volcano covered by a thick layer of ice caps. The most explosive phase lasted a week, from the 14th to the 21st of April, which was estimated to be a VEI 4. The Fisher eruption caused 250 million cubic meters of ash blasted 11,000 meters into the atmosphere. In Iceland, the eruption did not cause any deaths or casualties. However, the eruptions caused 150-meter thick ice caps to melt, which led to flooding. It destroyed a highway, while ash contaminated the rivers with high concentrations of fluoride and caused blockages. 20 farms were destroyed by the flooding and ash, and there were health concerns for the local farmers and livestock that were in close proximity to the volcano. The major impact was internationally, however, as winds distributed the fine-grained ash over continental Europe and stopped flights from taking off. In a matter of hours, Eyjafjallajökull brought our modern high-tech world to a juddering halt when the European aviation authorities were forced to shut the skies, causing severe impacts on the economy worldwide. Iceland was prepared for this eruption because of the first small eruption that occurred on the 20th of March. They were able to predict that a larger eruption was coming. A warning system with text was being sent to residents with a 30-minute warning, which allowed them to evacuate the 600 locals that resided in the exclusion zones during the eruption. Furthermore, the government paid to dredge rivers, or allowed them to flood and create new paths. They also bulldozed the other roads to allow the flash flood water to reach the sea without washing away bridges. After the eruptions, Iceland was also able to recover quickly. However, Iceland was not able to control the large amount of ash that was created from the eruption that had severe economic impacts. Overall, Iceland did an excellent job mitigating this hazard, as all aspects of the hazard mitigation were achieved efficiently and effectively. On the other side of the world, you have Mount Merapi. Mount Merapi is one of the many volcanoes on the Indonesian island of Java, located on the Pacific Ring of Fire, a series of fault lines surrounding the Pacific Ocean. Like the Icelandic volcano, Mount Merapi is a stratovolcano. However, it is extremely active, spewing out smoke 300 days a year, and erupting once every 5 years. This is very dangerous for the neighboring villages, who find a strange attraction to the mountain. According to local myths, the Palace of Spirits resided in Mount Merapi. Hence, locals would regularly bring offerings to the mountain, praying that the mountain would remain calm. However, their efforts had been to no avail, as the mountain erupted in 2010. On the 25th of October, the Indonesian government raised the area's alert level to its highest, as 3 major eruptions occurred on the mountain. All 32,000 people living within 10 kilometers of the volcano were told to evacuate. As the pyroclastic flows reached rivers 4 days later, sand and volcanic ash also covered everything nearby. To combat this, a group of 400 volunteers was formed. The volunteers had 2 main tasks. 1, to warn communities of incoming dangers, and 2, to provide food for displaced villagers. By November, most air services to and from the area had been suspended, thanks to the expanding volcanic ash plume. Although the volcano is said to have stopped erupting on the 30th of November, the government of Indonesia still maintained an exclusion zone within 2.5 kilometers of the volcano. 9 villages remain in restricted areas. In all, the volcano had taken the lives of 353 people, mostly in the form of burns. International aid came swiftly during the disaster. Countries such as Japan, Taiwan, the US, and Canada donated over $5.8 million. However, recovery had been too slow, and before long, Merapi erupted again in 2013. Violent volcanoes have been around for a very long time, and they're not going to go away. So what on earth does the future hold? At present, scientists are monitoring around 100 of the world's 550 active land volcanoes. 15 supervolcanoes have been singled out for special study. Our modern world has never experienced a truly massive volcano eruption. The last VEI 8 explosion, the Toba supervolcanic eruption, occurred around 75,000 years ago, leading to the eradication of 60% of the human population and causing a genetic bottleneck in humans. but another one may soon be due. Geographers reckon that 2 VEI-8 eruptions could happen every 100,000 years. Some warn that a big one is already overdue, and it wouldn't be a pretty sight. The ashy aftermath of a really big explosion could blot out the sun of years on end. No sun would mean no plants, which would mean no food. So should we be worried? Are we living on borrowed time? What if the next big one happens soon?